I'm Ayansui, the team captain. I'm responsible for the hardware and electronics of our robot, including our two microcontrollers, the OpenMV camera and the Raspberry Pi Pico 2W, as well as the integration of the other sensors.
Hi, I'm Tanash, and I'm the main programmer of our team. I'm responsible for programming both the microcontrollers, including the Raspberry Pi Pico 2W and the OpenMV S7 Plus. Our journey began in middle school when we attended EV3 robotics classes and learned the basics of building and programming robots. Through these classes, we discovered each other's strengths, whether in programming, hardware design, problem solving, or research. Realizing that our skills complemented one another, we decided to form a team. Since then, we have worked together to learn, innovate, and compete in robotics competitions.
Our robot uses a dual controller architecture built around an OpenMV S7 Plus camera and a Raspberry Pi Pico 2W. The system combines computer vision with distance, gyro, and RGB sensors for accurate line tracking and victim detection. The robot has 6 DC motors and 1 servo. 4 DC motors are used to control the 4-wheel drive train, and 2 DC motors are used to control the 2 claws independently, while the servo is used to lift the arm. We started by building a LEGO EV3 robot that used Arduino and OpenMV controllers to complete the task. However, after extensive testing, we found several limitations. The robot struggled to climb large speed bumps, cross wide gaps, and complete the ramp of death because it used tracks. As a result, we decided to develop a fully open source robot that would be completely autonomous and capable of handling all challenges more effectively. We have made an open source robot that uses 2 OpenMV S7 Plus cameras and 1 Pico 2W. One OpenMV is placed in the center of the robot for detecting and following the line, and one camera is placed in front of the robot to detect victims and evacuation points. We have used several sensors like time of flight, 9-axis gyro, and RGB light sensors, all connected through an I2C multiplexer to Pico. We designed custom silicone wheels for a robot to improve its mobility. The shape helps the robot climb speed bumps, ramps, and seesaws. After testing 12 different kinds of wheel designs made from materials such as TPU, rubber, plastic, and silicone, we found that the star-shaped wheel design provided the best performance of silicone material. Our robot uses 4 6-volt GA25 motors with custom gearboxes running at 180 RPM. To increase torque and improve ramp climbing, we replaced the original gears with gears from a 12-volt 130 RPM motor. The left and right motor pairs are connected in parallel and controlled by a TB6612 FNG motor driver. 2 M20 DC motors driven by another TB6612 FNG motor driver independently control the claws for victim pickup. An MG995 servo is used to lift the arm. All of the robot's motors are powered from the main supply, consisting of 2 LiPos of 2500 mAh and 7.4 volts connected in parallel to increase the current. The Pico and OpenMV are powered by a single cell LiPo of 2500 mAh and 5 volts.
Our robot uses 3 main types of communications, including I2C, UART, and GPIO-based digital communication. We use I2C to communicate between the Pico 2W and the I2C multiplexer. To communicate between the Pico and our first OpenMV camera, we use the UART communication, and to communicate between the 2 OpenMV cameras, we use the GPIO-based digital communications. For line following, we use the downward-facing OpenMV camera placed at the center of the robot. It detects the black line, green markers, silver tape, and gold tile using the built-in block detection and more than 25 regions of interest. The robot combines this visual data to calculate values like line slope and deviation and converts them into a steering value from -100 to +100. When green markers are detected, the robot performs the required turn and then realigns itself back to the black line using the camera. To enter the evacuation zone, our robot detects the silver tape using the downward-facing OpenMV camera and then confirms it using an RGB sensor to avoid false positives. Once inside, the robot opens its arm and moves through different predefined paths while the front-facing camera searches for victims. After picking up a victim, the robot looks for the correct evacuation point, drops the victim there, and exits the zone by circling the perimeter and looking for the exit. For victim detection, we use the front-facing OpenMV camera with a custom-trained machine learning model. Once the robot enters the evacuation zone, the camera continuously scans for victims while the robot moves around. When a victim is detected, the robot approaches it and sends a command to the claw mechanism to pick it up. We also use embedded wires in the claw to confirm live victims after the pickup. To detect victims in the evacuation zone, we developed and trained our own AI model using Edge Impulse. We collected and labeled images from different victim types, then trained a lightweight computer vision model optimized for real-time performance. The model runs on our robot and allows the front-facing camera to automatically identify victims, enabling faster and more reliable detection during rescue missions. For our future plans, we want to improve both the speed and the intelligence of our robot. We plan to train a better AI model for the evacuation zone so that the robot can detect and classify objects more accurately. We also want to shift towards a Linux-based software using Raspberry Pi, OpenCV, NumPy, etc., which will allow us to create more complex and efficient algorithms for faster runs.